Hello and welcome to the Introduction to Energy lecture. So you can see these questions in front of you. These are the ones that we will answer today. What is energy? What is the first law of thermodynamics? What are some of the forms of potential and kinetic energy? And how can energy be converted from one form to another? So there was a video posted, and I'm not going to play it here, but it is posted on the course website, and I encourage you to watch that before watching this video. So very basic beginning here. What is energy? There's the sort of physics definition of energy, the way physicists think about it, scientists think about it, and technically it's the ability to do work. So work is the transfer of energy from one location or one form to another. So energy is the ability to do work, and work is the transfer of energy. So it's kind of this circular definition. But we're more concerned in this class with the practical implications of what energy is. So energy does things for us. It makes things happen, as Hank says in the video. So energy is in everything all around us all the time. We cannot physically do anything without energy. The fact that you can hear me right now, the fact that you can see this screen, the fact that you can sense anything around you, that all requires energy. And the things that you sense all are evidence of energy in some way, shape, or form. So energy is literally around us all the time, everywhere you look, every millisecond of the day. Okay, so nothing happens that we can perceive as humans without energy. Nothing happens. Nothing moves, nothing makes a sound, nothing is bright, whatever. Okay, so energy makes things happen. It does things for us. So some examples of things that use energy, I mean, it's almost infinite, right? So everything, literally everything that we can perceive as human beings has energy. Some things that you normally think of having energy, like a battery, the sun has energy, a light bulb can generate or emit energy, a furnace can emit energy. You can look at how much energy is used in the planet, how much the human body is using at any given time, how much a building is using. So energy, you know, I could go on and on and on. It's everywhere all the time. Everything that we know that we can perceive as humans uses energy. So I want you to think about that, or to consider that as we move forward, that energy is absolutely everywhere all the time. So I also want you to understand that energy, not only is it around us, but I want you to think of it in terms of an amount, a quantity, right? So energy is an amount of something. So energy is not just this sort of hypothetical, like we know it's there, we're not really sure what it is. We can actually normally measure the amount of energy, and so we can measure, do you have a little bit of energy, do you have a lot of energy, do you have even more energy, and so forth. But we're not used to thinking in terms of amounts of energy so much, like we would think of, say, an amount of money, or even an amount of time. Or an amount of, I don't know, apples. So an amount of food. So we're used to thinking of certain things that are physical. They're like, hey, I have a certain amount of food here, and you have more food than me. So those are just two different amounts of things. And it may sound silly to use that example, but we're used to thinking of things in that way. But energy, we can also think of that way. And I want you to keep in mind that energy is an amount. It's a physical amount of something. And I'll just go over a couple of examples here just to kind of drive that point home. So if you have 1 gallon of gas, okay, so you have a certain amount of energy. It's not a whole lot, maybe 100,000, a little over 100,000 BTUs, give or take. But if I give you 100 gallons of gas versus 1 gallon of gas, you know that since gasoline contains energy, so if you have more gas, that means you have more energy. Again, energy is an amount of something. I want you to think about that. It's an amount of something. So if I give you a toothpick, this does have some energy in it, but if you compare that to a whole cord of wood or a couple of cords of wood, you know that there's way more energy in that wood than there is in this little piece of wood, right? They both contain energy. But if you have more wood, you have more energy. Again, I just want you to think of this in terms of quantities. And then the last example here, if you burn one match and you have the heat from it, there's some energy in there, right? Well, compare that to, a house that's on fire or a giant fire. So fire contains energy. Fire is energy, really. So if you have more fire, that means you have more energy. The whole point here, obviously this is very redundant, but the point is that energy is an amount of something, so you can quantify it. You can have a little bit of it, you can have a lot of it, in all points in between. So the point is that I want you to consider that energy is an amount of something. We can quantify it, okay? Just like we can quantify anything else. Okay? All right, so that's real basic intro to energy. Now we're going to discuss thermodynamics. Thermodynamics is just, it's a fancy way of saying how it's the study of how energy moves in and between systems. So anytime you are analyzing the movement of energy within a system or between systems, you're engaging in thermodynamics. It's a fancy way of saying studying how energy moves around. Okay? So the really important thing to know here is the first law of thermodynamics. This is important to understand. I'm sure you've heard this at some point in your life. Energy cannot be created or destroyed. It can only change forms, or often referred to as the law of conservation of energy. This is fundamental to understanding thermodynamics and to understanding energy. And that is that any energy that you see came from somewhere else, whether it's the energy that your body is using to hear and understand what I'm telling you, the energy that is used to generate the light coming out of the screen that you're looking at, that's all energy, and that all came from somewhere else. Okay, so energy never goes away. It only changes forms. We'll kind of get into some more details here in a minute, but that's the first law of thermodynamics. So if we, and again, I'm sure this is a review for most of you, but the two basic categories of energy are potential and kinetic. Potential can be thought of as stored energy. Kinetic can be thought of as energy of motion. Okay, so there's a number of different forms within each of these types of energy. So with potential, we have nuclear, chemical, mechanical, and gravitational. So nuclear energy is contained within the nuclei of all atoms. Okay. So anything that's made of atoms, which is, again, everything that we perceive, that has nuclear energy inside of it holding the atoms together. Chemical energy is the energy that's in the chemical bonds that holding one atom to another atom. So basically, like a water molecule, for example, you have a hydrogen and two oxygen. There's a bond there, a chemical bond that holds them together. There's chemical energy inside that. Everything that is made of more than one atom has some chemical energy in it. So anything physical, you can think of it has some chemical energy in it. Mechanical potential would be something like compressed air, a wound up spring, a stretched out rubber band. So that's physical, sort of what we think of as like physical energy that's, again, it's being stored and ready to be released. Gravitational is the energy, the potential energy of anything that's above the ground, basically. Okay, so if you push something off a table, it's going to fall. That gravitational is then converted into another form of energy. So our forms of energy of motion: electrical and electromagnetic or radiant. We have thermal, motion, and sonic. So electrical is just the movement of electrons through a wire. That's electricity. Radiant, all things, everything above absolute zero. So anything with any temperature at all has radiant energy. It's radiating these waves of energy out in all directions. Thermal energy is actually the energy within any matter that has any temperature at all. So anything that, again, that's above absolute zero, the molecules are actually vibrating, and that's thermal energy. So it's these vibrating of molecules that you cannot see because so it's so small. But that's thermal energy. Motion, kinetic is just anything that's physically moving, ball rolling down a hill, a car rolling across the road, wind blowing through the air, anything that's moving. And then sonic energy is sound waves that can come from anything, but that's waves that actually travel through the air, and that's sonic energy. So the potential energy, these are all stored. So these are not sort of doing anything active. These are all stored, and they can be used to do other things. Kinetic energy is all energy of motion, so they're actually actively doing something, whether it's a moving electron, a moving sound wave, a moving electromagnetic wave, and so forth. Okay? So these forms of energy are constantly being converted into one another, all the time, all around you, all the time. You can press pause and look around you right now. There's probably 20 things 20 examples of energy being converted around you. Whether it's a sound hitting the wall and then increasing the thermal energy in the wall, and then that wall is then radiating that energy back out, which then goes up and is absorbed into the ceiling, and that absorbs and radiates. So, I mean, there's just energy constantly being converted all the time. Okay, so I want you to keep that in mind. These forms are around you all the time, and they're constantly, again, based on the first law of thermodynamics, when one of these forms is converted into another form, you never lose it. It goes into a different form. Okay? So, I want you to do a little mental exercise here. We will do this in class, but I want you to think about a clock like this that's hanging on the wall, battery-operated clock that's hanging on the wall, and think about how many of these forms of energy are in this clock when it's hanging on the wall. So we'll go over this in class. Go ahead and press pause and think about it, and then we'll do this when I see you later. Okay, so there was a video on energy transfer posted on the course website, so I'm not going to play that again, but I suggest you watch that if you haven't watched it yet. And there should be a hyperlink if there's a PDF of this PowerPoint posted. But what it kind of some of it boils down to is that all of the energy that we use, just about all of it, comes from the sun. Okay, so we'll take a look at that in a moment. We'll discuss this further in class. So in order to go through a little thought exercise, and I want you to think about this. I want you to trace the energy conversion, okay, of these three things from the actual form that's listed here, and then I want you to trace it backwards. Like, where did the energy come from for each of these? And I'll give you an example in a second. Because remember, the first law of thermodynamics dictates that all energy came from somewhere else. So anytime you see energy, whether it's the sound of my voice, whether it's your car moving down the road driving to school, whether it's a projector, or so let's say the screen that you're looking at, the light coming from the screen. So all of those are forms of energy that came from somewhere else. So we'll do this exercise in class, but I'm going to give you an example with the sound of my voice. So remember, what I'm trying to do here is start with the sound of my voice, and then I'm tracing just the energy, just the energy back to where, as far as I can go. Okay? So, first we have sound waves, right? So sound waves are sonic kinetic energy. Just moving air, it's these waves that are moving through the air. Okay? If you think about where that came from, the sound itself, so the energy in the sound waves comes from the mechanical motion kinetic energy of my vocal cords vibrating, right? So again, we're just looking at the energy here. So the vocal cords physically vibrating, that is motion energy, and that is what actually causes these sound waves, which is another form of energy. So where did I get the energy to move my vocal cords? I'm sure there's some more. I'm not a chemist or a biochemist or whatever. I'm sure there's more going on with cellular level, mitochondria, and all that sort of stuff. But ultimately, any energy that I expend, it comes from the food that I eat. That's where I get my energy, right? I'm not a photosynthetic, so I get my energy from food. So food is chemical energy, okay? So we use that chemical energy that, again, we're just looking at the energy. So the energy in the food is what ultimately we use to vibrate our vocal cords. So where did the food get its energy from? So let's say it's meat, like bacon or whatever. So animals get their energy from plants. Now, of course, some animals eat other animals, and that's all well and good, but the animal that they ate got their energy from plants. So ultimately the point is all living creatures, well, not all living creatures, all animals get their energy from plants, ultimately, right? So where do plants get their energy? Well, they get it from sunlight, okay? And so the point here is not that I particularly care about where the energy came from in the sound of my voice, but that you understand that my voice coming out right now is energy. So the sound waves are energy. That energy came from somewhere else, and that energy came from somewhere else, and that energy came from somewhere else, and so forth. And you can pretty much, most forms of energy trace back to this. Almost all examples of energy all around you right now came from the sun. And we'll go over that in class in more detail. I also want to point out that these arrows, okay, so we go sunlight to the vegetables, vegetables to food, food to the vocal cords, and so on. You notice that the arrows get smaller as you go up. That's because every time you convert energy from one form to another, you lose some of the energy. So there's no such thing as 100% efficient energy conversion. And we'll talk about that later in more detail when we talk about the second law of thermodynamics. Okay? But the point here is that all energy comes from somewhere else, and you can always trace your energy from somewhere else. And I could look at where the sunlight came from. I mean, that's nuclear fusion energy, and those hydrogen atoms came from somewhere else, and we could keep going on and on. Okay? All right, so that's it for this intro to energy. So remember, we talked about what energy is, what's the first law of thermodynamics, what are the forms of potential and kinetic energy, and also how can energy be converted from one form to another.